Hi everybody. So today I wanted to make a video that brings together a whole bunch of the big picture concepts of why we're sort of interested in the optical properties of minerals and what they can tell us. These ideas have been scattered around in our other videos, but I really just wanted to bring them all together in one place so that it's a little bit more straightforward what's going on here. In order to do this though, we kind of have to go back and relook at some basics of what you might learn in a mineralogy course, and what better place is there to start than actually defining what a mineral is. There are 5 main characteristics which define a mineral, some of which are a bit squishier than others, but for our purposes, the definition we'll use is that a mineral is a naturally occurring, inorganic, solid, that has a definite chemical composition, and an orderly internal arrangement of atoms. And really, the pieces of this definition that are going to matter a lot to us today as we go forward are that definite chemical composition and the orderly internal arrangement of atoms in a mineral, which gives a mineral structure. So with the definition of a mineral fresh in our mind, let's go and look at some of the larger concepts that we've talked about before in our other videos. So this triangle of concepts may be familiar to you, but now that we've thought about the definition of a mineral, let's add a bit more to it. So, all of these concepts are going to be derived from the chemistry and the structure of a mineral. And the simplest way to sort of think about this is probably to do an example. So, as you've probably guessed, given my love of corundum, today we're going to talk some more about corundum. So when I say corundum, what I'm actually saying is the mineral with the chemistry aluminum oxide, Al2O3, and with the structure of having oxygen in a hexagonally closest packed arrangement, and then having aluminum occupy 2/3 of the octahedral interstices between those oxygen atoms in the hexagonally closest packed arrangement. So it's a lot easier just to say corundum than all the other things I said that actually are the definition of the mineral corundum. But it's important to always remember that chemistry and structure are really what are defining corundum. So let's go for a bit deeper dive into the chemistry and structure of corundum and how those two concepts actually interact with one another. So let's start off looking at the chemistry of aluminum and oxygen, which are going to bond together to make our corundum. So, in thinking about the type of bonding that's going to occur between aluminum and oxygen, we want to think about the concept of electronegativity, and that is the ability of an atom to attract shared electrons. If there is a large difference in electronegativity between our elements, then bonding is predominantly ionic, and if there is a relatively small difference in electronegativity between our elements, then the bonding is either covalent or possibly metallic. For aluminum and oxygen, the difference here in electronegativity is large enough that we're going to predominantly think about this as an ionic bond. So, let's make some ions. Oxygen is going to want electrons a whole bunch more than aluminum is, and given their respective positions on the periodic table, aluminum has 3 electrons to give up, and oxygen will gain 2 electrons in order to fill its electron orbitals. This also provides the stoichiometry for our corundum, the relative ratio of aluminum to oxygen in order to maintain electrical neutrality. So we need 2 aluminums and 3 oxygens in order to get 6 positive charges and 6 negative charges balancing to 0. So we've got the chemical formula now for corundum, and we can see where that has come from, but let's go and build the structure of corundum as well. Thankfully, for substances where ionic bonding is predominant, we can actually build these structures fairly simply by imagining our ions as spheres of different radii and then figuring out how to pack them according to a series of rules known as Paulings Rules. This is a simplification from reality, but it actually works pretty well for our corundum crystal structure, and so we'll go forward in this vein. So our aluminum cation is going to be small compared to our oxygen anion because the aluminum has given up electrons, whereas the oxygen has gained them. So the ionic radius of our aluminum 3 plus is going to be 67.5 picometers, and the ionic radius of our oxygen 2 minus anion is going to be 126 picometers. Since our oxygen is larger than our aluminum, let's first think about how we could pack together our oxygen as tightly as possible before we start to think about bringing in the aluminum into the structure. So this creates a geometry problem in which we try to pack together spheres as efficiently as possible into a three-dimensional space. And there are two answers to this problem that have maximum efficiency of packing spheres together in a space. One is called hexagonal closest packing, and the other is called cubic closest packing. So the best way to explore this concept further is to take a look at some models made of marbles. These marbles are all approximately the same size, representing oxygen anions, and right now these are held together with hot glue. So if we were only interested in one layer of our structure, this would be the most efficient way to pack those marbles together in a single layer. But as we expand this structure to multiple layers, things get a bit more complicated. In order to most efficiently pack these spheres together, we're going to take advantage of some of the void spaces we see in this first layer. And there are two different types of gaps where our second layer may most efficiently nestle in to this layer of spheres. The first is represented by this upward-facing dark blue triangle. And after we find one of these spaces, a whole bunch of others become apparent as well. And these repeat neatly in a geometric pattern throughout our first layer. But we also have some other gaps in the structure, which are going to be best represented by a red downward-facing triangle. And once we spot one of these, it becomes easy to spot some others, which repeat in a similar geometric pattern throughout the structure. So our second layer that we add to our structure is going to be exactly the same as the first. However, we're going to get to choose whether it sits in the voids represented by the blue triangles or the voids represented by the red triangles. So let's grab another layer of some marbles held together by hot glue, and I'm going to choose to try and nestle this layer into areas where we saw the red triangles earlier. That was probably a bit hard to follow, so let's bring back a map of where our void spaces were from our first layer and superimpose it on this image. And we can see indeed our second layer is nicely nestled into the voids represented by the red downward-facing triangles. So let's now think about the map of the void spaces we're going to have in our second layer here in our structure. And here's where we're going to end up with a choice that's going to matter for our structure going forward. When we bring in our third layer, if we choose to align it with the voids represented by our blue triangles, we will effectively end up with a repeat of our first original layer. Let's take a look at that here. So we've added in our third layer, and you should notice that it's directly comparable to the first layer we had in our structure. As we did before, let's take a map of the void spaces in our second layer and superimpose that over our third layer, so you can indeed see that the third layer is nestled in the void spaces associated with the dark blue triangles. And this is actually all the information we need to describe a hexagonal closest packed structure. The hexagonal closest packed structure just continues this repetition of layers. Our first layer is referred to as A, and then there's a second layer nestled into the voids of that original layer. This second layer is referred to as B because it's not the same as the first layer in its placement in the structure. And then our third layer is placed in such a way as it repeats our first layer. And this is based on the choice of which set of voids in that second layer to nestle our third layer into. So let's go back now and take a look at what would have happened had, instead of choosing the voids associated with the blue triangles to add our third layer into, if I chose the voids associated with the red triangles. So now our third layer in the structure is aligned with the voids associated with the red triangles for our second layer. So once again, let's superimpose a map of the void spaces from our second layer onto our third layer so that we can confirm they are located appropriately. And you can see that the third layer is indeed filling in the void spaces associated with the red triangles of our second layer. This might seem like a fairly trivial difference, but it's actually really substantive. And so what's actually happened here is we're no longer repeating the structure after two layers. And in fact, each of these layers is distinct in this structure. And only by adding a fourth layer would we eventually see the repeat in this structure. This is known as cubic closest packing, and it's often abbreviated by ABC as the structural arrangement of layers. We'll take a deeper dive into cubic closest packed structures with the mineral spinel, but for now with corundum, we'll focus on hexagonal closest packed structures. So we've thought about ways in which we could pack together spheres of equal radius that in this case are going to be representing our oxygen anions in the corundum structure. But let's go back to the beginning and actually think about now where aluminum is going to end up in this structure. So even when these spheres are packed together as efficiently as possible, there are still going to be void spaces in these structures. And there are going to be two different types. We can get an idea of these two different types by going back to the beginning when we looked at the different void spaces in our structure and thought about how we were going to add our second layer of marbles on top of these in order to pack them as efficiently as possible. We chose to add in our second layer of marbles atop the void spaces associated with the red downward facing triangles. And this choice generates two different types of sites left behind where we may be able to place our much smaller aluminum. The red downward facing triangles are going to be tetrahedral sites, and the blue upward facing triangles are going to be octahedral sites. Let's isolate examples of each of these sites from our larger structure so that we can learn a bit more. So our tetrahedral sites are going to consist of 4 marbles surrounding a void space that is associated with one of the downward facing red triangles. Here's an example of one of these sites isolated from the rest of our structure, and at the center of this is a tiny bit of void space that remains after we've nestled our marbles in as efficient a packing arrangement as possible. You can sort of see it there, just a little tiny void space right in the center. This is called a tetrahedral site because that is the shape that would be generated if we imagine planes connecting our marbles together. So from this, I want you to get a sense that there is a geometric relationship between the size of that void space that remains and our marbles that we're packing together in as efficient an arrangement as possible, because there is. But for right now, you should have the general sense that, hey, any sphere that I wanted to put inside our tetrahedral site is going to have to be pretty small. So we also have another site left in this structure, and that is an octahedral site. So here is one of our octahedral sites that has been removed from the larger structure as a whole. This octahedral site consists of 6 marbles surrounding a central void space that is associated with one of the upward-facing blue triangles in our previous diagram. As with the tetrahedral site, the octahedral site is so named because if you were to connect all of the marbles together with planes, you would end up generating an octahedral shape. Although it may be a little bit hard to tell just off the bat here, the octahedral site is actually better suited to house larger spheres than the tetrahedral site is. So given the tetrahedral and octahedral sites that currently exist in our hexagonal closest packed arrangement of oxygen anions, is there a location where aluminum can fit? We can answer this question by using one of Paulings rules and taking a look at the radius ratio between aluminum 3+ and oxygen 2-. Comparing the relative sizes of the aluminum and oxygen ions suggests that aluminum would be best suited in an octahedral coordination. meaning that our aluminum 3+ cation should have 6 neighboring oxygen anions. And it just so happens that our hexagonal closest packed arrangement of oxygen anions has those octahedral sites ready to go. These are sometimes also referred to as interstices, which means the spaces in between our oxygen anions. So we put some aluminum in the octahedral voids and all is well. Wait a second, we have this pesky chemistry stoichiometry thing going on here. How many octahedral voids are there to oxygen anions? Because in the end, we really do need to keep this 2 aluminums to 3 oxygens thing going on, or else our crystal gonna explode. So if we take a look at the ratio of octahedral voids to oxygen atoms, we will find that there is 1 octahedral void per oxygen atom. And so we're going to have to leave some of those octahedral voids vacant in order to maintain our stoichiometry of 2 aluminum atoms to 3 oxygen atoms. So let's go back to a marble model and see how this all plays out. Here we have a single layer of marbles representing oxygen anions in the beginnings of our hexagonal closest packed arrangement. And what I've done here is add metal ball bearings, which act as smaller spheres representing our smaller aluminum ions in this structure. I also expanded the dimensions of this layer a bit so that you can better see the pattern that is going on with our aluminum ions in this structure. So how did we generate this pattern for the placement of our aluminum cations in this structure? If we think back to the different types of voids that are present in this first layer of our hexagonal close-packed arrangement of marbles, we recall there are 2 different types, and depending on how I add the second layer of marbles onto this first layer, one of these series of voids is going to become tetrahedral sites, and the other is going to become octahedral sites. We'll nestle the second layer of marbles into this structure such that the red triangles become our tetrahedral voids, leaving the blue triangles to be our octahedral voids. Because of our relative radius ratios of our aluminum to oxygen, we know that the aluminum is going to be best suited in an octahedral void, and so we now have a map of sites where aluminum would be happiest. But we can't forget about our stoichiometry, and so that means we actually have to leave 1 in 3 of these sites vacant in order to maintain 2 aluminum atoms to 3 oxygen atoms in our structure. So the first series of vacancies I selected somewhat randomly, but that will then propagate through our following layers in the corundum structure. So let's focus on the pattern of our aluminum cations as we continue to build this structure. We already know how our hexagonal close-packed marbles representing our oxygen anions are going to stack. And after 2 distinct layers, layer A and layer B, we actually have enough information to describe the hexagonal close packing of these marbles. And if aluminum had been present in all of the octahedral voids, we would already have a fully described corundum structure. But the propagation of those vacancies throughout our structure actually make this a bit more complicated than it may first seem. Here's an overlay of green semicircles in the positions currently occupied by aluminum ions in this second layer of our structure. And now let's add the positions of our aluminum ions from our original layer. And so we haven't yet repeated the structure in terms of our aluminum ions, and so we're going to have to add on some more layers before that occurs. So let's add a third layer to our structure, once again focusing on the positioning of our aluminum cations within. When thinking about only the glass marbles that are representing our oxygen anions, this layer is simply a repeat of the first in our structure. But the metal ball bearings representing our aluminum ions still have not repeated yet in this structure. Here's an overlay of purple semicircles for all of the positions of aluminum ions in this layer. And now we'll bring back the positions of the aluminum ions from the previous 2 layers. And we still haven't yet repeated the pattern of aluminum ions in a layer as yet. Not to drag this out any further, the next layer will actually repeat our pattern of aluminum ions in this structure. So it takes 3 distinct layers in order to fully express the pattern that is occurring with our aluminum ions in this structure. So you may think, well, great, we're going to need 3 layers in order to fully express what's going on in our corundum structure, but because our hexagonal close-packed oxygen is repeating every 2 layers, and the pattern of our aluminum ions is repeating every 3 layers, in order to fully express the pattern that is going on with our corundum structure, we're actually going to need 6 total layers. There will be 6 unique layers before we start to repeat. So let's build ourselves a tiny corundum crystal. So here's the first layer in our structure. We'll call this layer A1. A referring to the hexagonal close-packed oxygen, and 1 referring to the pattern in our aluminum ions. Next up then would be layer B2. Our oxygen will then repeat, but our aluminum will not, so we end up with A3. And now our aluminum finally repeats, but our oxygen will not, so now we're to B1. Hopefully you haven't turned off the video and run away yet, because next up we have exciting A2. And at the end, we finally have our last unique layer of B3. Adding an additional layer after this would bring us all the way back to A1. So we've now built a tiny corundum crystal. Hooray! And now for the part of the story where I'm in a bit over my head, because we're going to talk about space groups. And so what we're going to delve into now is the symmetry represented in our corundum structure at this scale. If we imagine our structure infinitely repeating in all directions through space. So the space group of corundum is R, 3 bar, 2 over C. Sometimes this is shortened to R, 3 bar C, but they mean the same thing. Here's a 2-dimensional representation of the symmetry elements in our 3-dimensional structure. So as is often the case when representing a 3-dimensional structure in 2 dimensions, this is a projection of the various symmetry elements that we can see. And in this case, the tiny fractions that you see associated with our various symmetry elements are actually telling us the height within the 3-dimensional structure along the C crystallographic direction that these symmetry elements are located. For a deeper dive into all of this, you should check out the website in the lower left corner of this figure. There you can go through all 230 space groups in gory detail. One other quick note, the symbols that I use for some of the symmetry elements are a bit different than the ones shown here. 2-folds here are represented as arrows, and 2-fold screw axes are represented as half arrows. In my diagrams, these will be represented as ovals and ovals with wings, respectively. So what is the space group R, 3 bar, 2 over C? This is one of 230 possible ways in order to build structures that repeat in 3-dimensional space. So let's translate what R, 3 bar, 2 over C means. R means that our structure will reference the rhombohedral Bravais lattice. 3 bar is telling us that the C crystallographic direction through our structure is going to have a 3-fold rotoinversion axes. And 2 over C lets us know that the A crystallographic direction through our structure is going to have 2-fold rotational axes, along with glide planes perpendicular to those axes that have a translational element along the C crystallographic direction of our crystal. And then in addition, there will be even more symmetry elements that are going on in our crystal. But for our purposes, we care mostly about what's going on with the C crystallographic axis and the A crystallographic axes. So let's go hunt down a 3-fold rotoinversion axis. I, and I imagine many other folks, have difficulty visualizing these elements in 3 dimensions when it comes to something as complicated as the corundum crystal structure. So this next part is a bit of an oversimplification. But the first thing I want you to notice is this first aluminum vacancy right in the center of our structure. If we drop down a layer and map out some aluminum vacancies, we'll notice the following pattern. Dropping down an additional layer would add the following vacancies to our pattern, and dropping down one more layer would take us back to our original position of our aluminum vacancy. Taken together, what shape would these vacancies create in a three-dimensional space? A rhombohedron. And one common symmetry element that rhombohedrons are associated with is a threefold rotoinversion axis. So I think we've caught our threefold rotoinversion axis for now, and so let's just label that nicely. We'll call that the C-axis for our very tiny crystal. But actually for a space group, you wouldn't just be imagining this very tiny crystal. Instead, what you'd imagine are infinite planes as this structure repeats through space. And so there will be a whole bunch of these threefold rotoinversion axes if we imagine this infinitely extending in all directions. Just a bit of a difference to note when we're thinking about the discrete crystal versus the infinite repeating pattern in 3 dimensions that is the space group. So we figured out the 3-bar portion of our space group symbol. Now let's hunt down the 2/c portion of that symbol. And in order to do that, let's change the orientation of our structure a bit. So if we change the orientation of our structure by 90 degrees, we should be able to start to visualize where some twofold axes may exist in this structure. So with the marbles representing oxygen being so large, it's a little hard to actually see where our metal ball bearings representing aluminum are in this structure. So here's an overlay to help deal with that issue. And once we see this, we notice there are a couple locations where twofold axes exist in this structure. So one set of twofold axes is located here, and I'm going to label those our A crystallographic axes. Technically, there should probably be a couple more layers on the bottom of our crystal in order for those to be our A crystallographic axes, but my crystal was getting a little unwieldy, so you'll just have to imagine those. And then once again, when we go from thinking about the discrete crystal to the infinite space group, we can see equivalent twofold axes in other locations as well, as we imagine this structure repeating infinitely through space. Also, let's put on a representation of our C crystallographic axis so that you can see the relationship between our A crystallographic axes and the C axis of our crystal in this direction. The A axes lie in a plane perpendicular to our C crystallographic axis. So we've dealt with the 3-bar and the 2 portion of our space group symbol. Now let's take a look at the over C, and in order to do that, we need another adjustment in orientation. The over C portion of our space group symbol references a glide plane that will be perpendicular to the twofold axes we previously identified. Our glide plane will effectively act as a mirror plane, however with a translational element to our mirror images. And I think the best way to visualize this element is as follows. If we take a look at a portion of one of our marbles, here highlighted in yellow, we note that translated along the C crystallographic direction of our structure, we can find the mirror image of this portion of our marble, highlighted in blue. And as we travel along the C crystallographic direction, this pattern of translation and reflection continues. So that is one of the glide planes going through our structure. Now let's return to viewing our crystal structure along the C crystallographic axis to review what we've learned. When imagining our mineral structure model as a tiny crystal, the threefold rotoinversion axis that acts as the C-axis of our crystal would be as shown. In a perpendicular plane to our C crystallographic axes will be our A crystallographic axes, and these are twofolds within this structure. Here's a view of those relationships when rotating our mineral structure 90 degrees to look down one of our A crystallographic axes. Back to our previous view, perpendicular to these A crystallographic axes lie glide planes with a translational element along the C crystallographic direction. And those are the main pieces of our space group symbol for corundum, R, 3 bar, 2 over C. But to be honest, with our space group R 3 bar 2 over C, there are a whole bunch more symmetry elements we haven't even touched on going on in this structure at this scale. But it's also always important to remember that the space group is a representation of the symmetry in this structure as we extend to infinity in all directions. Still, we should be able to locate some additional two-fold axes, two-fold screw axes, three-fold screw axes, and inversion centers in this structure. But I don't really want to do that, so instead I'll leave you with this, which I'm about 60% certain I've lined up appropriately in our structure. And when we get to this level of detail, our marble model is not going to reflect the structure of corundum as accurately as we would like. This is because the aluminum voids in our corundum structure actually cause distortions in the hexagonally closest packed oxygen arrangement. Basically, the oxygens are not being pulled together by a positive charge whenever you have one of those aluminum vacancies, and so they end up being distorted slightly where those vacancies occur. But for some marbles, ball bearings, and hot glue, it's a pretty good representation of the corundum structure. So now that we've gone about as in-depth into corundum's chemistry and structure as we possibly could, let's just fiddle around with chemistry and structure a bit and see what happens. So there are many other metals with 3+ valence states, one of which is iron. And so what happens if instead of Al2O3, we take a look at Fe2O3? Fe2O3 also can have a structure with oxygen in a hexagonally closest packed arrangement and with 2/3 of the octahedral interstices containing iron instead of aluminum. And this is the definition of the mineral hematite. The structure of hematite is actually so similar to that of corundum that it is in the same space group of R 3 bar 2 over C. But the chemistry is different enough that these are actually two completely different mineral species. So there's an example of chemistry differentiating two mineral species. Now let's take a look at structure differentiating two different mineral species. So let's go back to our corundum definition, and from here we can go somewhere slightly different to the definition of alpha alumina, which is just another name for the same thing. But perhaps your corundum isn't natural. If it's synthetic, then technically it would actually be alpha alumina. But whether synthetic or natural, the chemistry and structure of either of these are exactly the same. However, not so when we introduce gamma alumina. And this is actually only a structural change. The chemistry here is exactly the same, but what has happened is instead of having oxygen in a hexagonally closest packed arrangement with 2/3 of the octahedral interstices containing aluminum, in this case gamma alumina has oxygen in a cubic close packed arrangement. This means that gamma alumina actually exists in an entirely different space group of F 4 over D 3 bar 2 over M. And this difference has important implications for our material's properties. So alpha alumina and gamma alumina are polymorphs. Their chemistry is exactly the same, but they have different structures, which cause them to be different species of, in this case, materials, since we're over on the synthetic side when we're talking about alpha and gamma. All right. So once again, the big take-home message is that chemistry and structure define a mineral. So going back to corundum and continuing on with this video, we've covered the chemistry and structure that define corundum, but now let's take a look at the crystallography of a macroscopic corundum crystal. So let's head to the lower left portion of our triangle of concepts. Here we have a fairly euhedral macroscopic corundum crystal. And when we think about symmetry on the macro scale, what we're going to think about is point group symmetry and not the space group symmetry that we were talking about earlier. However, point group and space group symmetries have many similar elements, so if you understood what was going on earlier with our space group, this will be a pretty straightforward what we're going to end up doing here. So there are 32 point groups, and let's take a look at the point group symbol for Corundum. The point group symbol for Corundum is 3 bar 2 over m. Wait a second, that sounds suspiciously similar to our space group symbol of r 3 bar 2 over c, doesn't it? And it is. All of our 230 space groups can be grouped under our 32 point groups. The point group 3 bar 2 over m can actually be composed of any of 6 different space groups. So what's going on here? When we transfer from the microscopic world, where we're thinking of infinite repeating patterns, and go into the discrete macroscopic world, what actually ends up happening is that some of our symmetry elements, such as glide planes, can't be expressed at this scale. Well, at least not as a glide plane. And so what ends up happening is that our glide planes become mirror planes, and if we have screw axes, those will end up looking like regular old rotational axes. There's a caveat there. There are some crystal classes where you could identify screw axes if you have very specific crystal faces, but that's a whole nother, let's not go there. Back to our corundum crystal, notice the hexagonal outline we can see in this view. Our crystal here has been a little roughed up. It's probably from a placer deposit, and you can see the edges have been abraded, and so the form is a little bit rounded off. But predominantly what's going on here, there is a tapered hexagonal prism, and it's being terminated by a pinacoid. And this crystal also has a couple other features modifying it, letting you know that the symmetry element that we're seeing here isn't as simple as a 6-fold rotation axis. A problem with using visible symmetry elements to determine our point group is that crystals of a lower crystal class or a less symmetric point group can sometimes masquerade as crystals of a more symmetrical class, depending on the particular crystal forms present. Basically, what I really need is a crystal form to cut both the A and C axes simultaneously for our corundum crystal, so that 3-fold rotoinversion axis can put in some work and show us an awesome rhombohedron. So given all that, in this direction, what we're actually seeing is the 3-fold rotoinversion axis of our corundum, and this is our C crystallographic axis. So we are looking down the C axis in this view. Our A axes will then lie in a perpendicular plane, and these will be 2-fold rotational axes. And then perpendicular to our A axes will be mirror planes. Go away, glide planes. No one can see you at this scale. There, much better. So let's rotate the crystal 90 degrees now, and we can take a look at the crystal viewing along one of our A crystallographic axes. So once again, what we're predominantly seeing here is a tapered hexagonal prism, but after I improve the focus, what you'll be able to see is, in addition to our hexagonal prism, it's also being modified by 2 very distinct planes cutting off the upper right and lower left corner of our crystal. So overall, our crystal looks pretty weathered, but these 2 planes, if we were to look at the faces here, are actually much fresher and much better looking than the rest of the crystal overall. These 2 planes are actually caused by parting in the corundum crystal. Whereas cleavage is a pattern of breakage caused by structural weakness in particular directions through a crystal, and is present in all examples of a mineral, parting is usually caused by other factors that don't necessarily need to be present in every example of a mineral. In the case of corundum, this is caused by either the exsolution or alteration of boehmite into very distinct planes in the corundum crystal structure. These boehmite to corundum contacts are then weaker than the structure overall, and so when these crystals break, they tend to break along these very nice, well-defined planes. Because the directions of these partings are actually crystallographically controlled, they're also telling us something important about the symmetry of our corundum crystal. And in the case of these partings, they're actually going to help us out a lot, because the partings will actually break into a rhombohedral pattern, allowing us to see the true 3-bar 2 over m symmetry of our corundum. Here you can see an image of a different corundum crystal where these planes of boehmite are very distinct. Taken together as partings, these 3 planes would generate a rhombohedron. Back to our original crystal, however, we only really have 2 of the total 6 different fractures we'd need in order to see a rhombohedron. But knowing that those 2 planes are actually part of a rhombohedron helps us to set where exactly our a-axes are for this crystal. Our a-axes will be 2 folds perpendicular to mirror planes, and in order to have that line up with our rhombohedron, they have to be located here. So we've tied down our crystallographic axes for 2 different views through our crystal. Let's also take a look at the mirror plane that we were talking about earlier, perpendicular to our a-axes, which will be located here in the corundum crystal. You can also see from this view how that rhombohedral parting is a bit fresher than the rest of our crystal. Let's take a look at some additional corundum crystals. Each crystal is a bit unique. However, when we combine the forms and parting directions, we should be able to identify the locations of our crystallographic axes for these crystals as well. In this crystal, it would be a little bit harder for you to mistake the C-axis as a 6-fold, given all the triangles we see here going on, which I think are some combination of both growth forms and then also the parting directions that we were talking about earlier. Here's a view down one of the A-axes for this crystal. Next up, we have a corundum crystal that displays parting rather well. It's had one very distinct break along one of those rhombohedral parting planes. And this is important to think about because when you have the shape of a crystal being determined both by its growth forms and something like parting, you can start to get some funky looking shapes, but as long as you understand what's going on and can kind of differentiate those 2 different forms in your mind, you'll be okay. So, back to the big picture. We've got our corundum structure and space group symmetry going on at the micro scale. We've got our macro scale corundum crystallography and point group symmetry. And it should be apparent at this point that our macro scale crystallography and point group symmetry are dependent upon what's going on at the micro scale. I mean, we'd only need to multiply the width of our microscale corundum crystal by about 7 million before we got to the width of the macroscale crystal shown. So let's do the same exercise, taking a look down one of the a-axes of our crystal. So we're looking at the microscale. Here's the same view at the macroscale with our crystal. And then here's those 2 views side by side. So while it's delightfully nerdy to look at how the microscopic structure of corundum influences the morphology of macroscopic crystals of corundum, it's a bit more important than just that. We can actually use this to our advantage, because the microscopic structure of corundum is going to control a whole bunch of different physical properties that vary with direction in the mineral. And not only physical properties, but chemical properties too. So properties that vary with direction in our crystal can include things like hardness, thermal conductivity, electrical conductivity, our optical properties, which is what we're going to focus on here, rates of various chemical reactions, and cleavage in addition to others. So going back to our triangle of big picture concepts, if we know that we have the mineral corundum, and we have a nice macroscopic crystal where we can identify the crystallography, I can tell you the optical properties that we'll see based on that knowledge. So this order of using our triangle of concepts is useful if you're someone like a materials scientist. In that case, you likely know the material you're working with, and if you can identify the crystallography, you can then utilize that material for specific physical properties. From the standpoint of a geologist, you're usually combining the crystallography with some other sort of physical property, like the optical properties, in order to identify a mineral. But the bigger picture here is that because of how all of these concepts are related to one another, if we can figure out any 2 pieces of this triangle, we're usually able to figure out the third as well. So now that we've talked about the microscale structure and chemistry of corundum, along with the macroscopic crystallography of corundum, let's now turn to the optical properties. And our macro scale natural corundum crystal isn't going to cut it for optical properties. As you can see here, it's very much not transparent. And if it were, it would have been quite expensive. But luckily, there's a large amount of synthetic corundum on the market in various forms. I'm going to use some flame fusion synthetic corundum in order to investigate our optical properties. So this flame fusion synthetic corundum has been cut very specifically to highlight these optical properties. And we are currently viewing this sample with plain polarized light that is vibrating in a north-south direction. And you can also tell we don't really have many crystallographic hints going on here because our sapphire is indeed synthetic. And if you want a bit more depth as to what we're doing here, you can check out Optical Mineralogy Uniaxial Minerals video or Optical Mineralogy Improved Uniaxial Optic Axis Interference Figure video. But basically what we see here as we rotate our sample in plain polarized light is not really much of anything. So we're not seeing any pleochroism in this direction. The pleochroism would be observable as a change in color as we rotated the crystal here. For this particular color of synthetic corundum, the lack of pleochroism is actually telling us the direction we are viewing through our crystal. But more on that later. So now let's choose a new viewing direction through our synthetic corundum crystal. So I'm actually going to take a moment and line everything up, appropriate for the flip that we want to do, and you'll see in a minute why I have to take this other additional little 90-degree rotation. So what we're going to do here is basically pick up the crystal and rotate it 90 degrees. And we can immediately see something interesting going on here. The color looks rather different in this direction. Let's now rotate our crystal with our new viewing direction and see if anything interesting happens. So as the crystal spins, we go from sort of a lighter raspberry color to a darker purple. That looked very similar to the original dark purple we started out with the other viewing direction. So what's this difference in optical properties with viewing direction caused by? If you guessed the microscopic structure of corundum, you are correct! So while these two videos aren't perfectly synchronized, take a moment and think about what is being illustrated as we rotate both our synthetic corundum sample and our microscopic corundum crystal structure. This direction through our crystal is where we have a threefold rotoinversion axis. And this symmetry element is actually responsible for the optical properties that we end up seeing in this crystallographic direction. A quick note on scale here as well. Energetic blue light has a wavelength of around 400 nanometers, whereas the width of our microscopic corundum structure is about 1.5 nanometers. Pleochroism as a phenomena occurs when there's differential absorption of different wavelengths of light as you travel through a crystal. But the threefold rotational symmetry of our crystal structure, coupled with the nature of light, prevents any differential absorption of light as it travels through our crystal in this direction, no matter how we rotate this crystal in this plane. It also means that light traveling through our crystal in this direction is only subject to one refractive index, and that refractive index is known as omega. So it's also important to note that even though we know we are looking down the c-axis of our crystal, given the optical behavior that we've seen in this direction, we can't pinpoint individual A crystallographic axes using our optical properties. But we do know that the plane of our A axes must lie perpendicular to our C crystallographic axis. So reorienting our flame fusion synthetic corundum by 90 degrees along with our microscopic corundum structure model yields the following results. We note a change in color with the reorientation of our synthetic corundum sample, and this change in color is a result of our plane polarized light interacting with a different direction through our corundum crystal structure. This change in color is associated with a different refractive index as light travels through this direction of our crystal, known as epsilon. Spinning the corundum sample here yields pleochroism as we return back to the darker purple color associated with refractive index omega. So I hope this demonstration has helped you understand how the microscopic crystal structure of corundum actually leads to the optical properties that we see at the macro scale. A three-dimensional representation of the different refractive indices caused by our microscopic crystalline structure is known as an optical indicatrix. Here's a representation of the optical indicatrix for corundum. This is highlighting the two different views through our optical indicatrix that are equivalent to the views we've taken through our flame fusion synthetic corundum. And once again, our optical properties and our optical indicatrix are a result of the corundum crystal structure. Looking down the c-axis of our crystal, that means that we can only see refractive index omega in this particular plane, and so we're not going to be able to see any fun pleochroism in this direction. Looking down anywhere in the plane of the a-axis of our crystal, well, we'll be able to transition between refractive index omega and refractive index epsilon, depending on how we rotate our crystal in this particular plane, and so we can see fun effects like pleochroism. So the big picture of the big picture video is that we can tie together all of these different concepts because of the chemistry and structure of our mineral. And that's what we did today in depth for the mineral corundum. Corundum as a mineral is defined by its chemistry and structure. These in turn determine the macroscopic crystallography that we can see in euhedral crystals. And the chemistry and structure also determines various physical and chemical properties that vary with direction in our crystal. Our focus is on how the optical properties vary, but we could have chosen others as well. Understanding the relationships between these concepts allows us to either identify unknown substances or to orient substances appropriately to take advantage of specific physical and chemical properties that vary with direction. Many high-tech applications require this type of knowledge, from developing quartz oscillators for wristwatches to developing monocrystalline silicon wafers appropriately oriented for the production of computer chips. Our modern world depends on crystalline materials and the anisotropy they display. So what all did we cover today? We talked in depth about the chemistry and structure of corundum, but in order to understand the structure of corundum, we first examined hexagonal closest packing, using a series of marbles held together with hot glue. These would end up representing the oxygen anions in our corundum structure. We used the radius ratio concept to determine where aluminum may be best suited in this hexagonally closest packed arrangement of oxygen anions, and figured out the pattern of aluminum that would be generated given our stoichiometric constraints on the ratio of aluminum to oxygen. We then put this all together in generating a microscopic marble model of our corundum structure. This structure has 6 unique layers before things begin to repeat. We talked about the space group symmetry that is present within our corundum crystal structure, the space group symmetry being one of 230 distinct ways to repeat a pattern infinitely through space. We then identified some of these elements in our microscopic corundum structure model. Here, the threefold rotoinversion axis is labeled as our C crystallographic axis. Once again, differentiating between the small discrete crystal and the infinite space group. We found some twofold symmetry axes perpendicular to our C crystallographic axis. These are our A crystallographic axes. And we also identified some glide planes in our crystal structure. Here's a view looking down the C crystallographic axis with all of these elements superimposed. And here's how our space group, R, 3 bar 2 over C, stacks up with our corundum structure model. From understanding our chemistry and structure of corundum, we then went to examine macroscopic crystallography. Taking a look at a fairly euhedral macroscopic corundum crystal and examining the point group symmetry of this crystal, we then identified the symmetry elements in our macroscopic crystal along both the C-axis and the A crystallographic axes, and compared the symmetry that we could see at the macro scale with the symmetry of our corundum structure at the micro scale. Our macroscopic forms and symmetry reflect the microscopic structure of our corundum. This began to bring our triangle of big picture concepts together. We then examined the optical properties of our corundum and how these relate to our microscopic crystal structure. Plane polarized light traveling along the C-axis of our corundum crystal will not be able to display pleochroism, as the light is only associated with one refractive index in this crystallographic direction as a result of the symmetry of our threefold rotoinversion axis as well as the nature of light. When we change the orientation of our crystal such that we're looking down the plane of the A-axis, we can observe the phenomenon of pleochroism as we rotate our crystal from a position associated with refractive index epsilon to a position associated with refractive index omega. We then talked about the optical indicatrix for corundum, which is a three-dimensional representation of these refractive indices, and how the optical indicatrix reflects the microscopic structure of our corundum crystal. We then wrapped everything up by going back to our triangle of big picture concepts and talking about how the mineral corundum is defined by its chemistry and structure, how the macroscopic crystallography is dependent upon that chemistry and structure, and how our optical, along with other physical and chemical properties, are also dependent upon that chemistry and structure. This helps us tie all these concepts together and also actually make use of them either to identify unknown substances or to take known substances and orient them appropriately to make use of specific chemical or physical properties that vary with direction. So thanks for watching this video, and I hope you learned something today. I certainly learned a lot in trying to make these videos. Part of the reason why mineralogy is a difficult course is just because there are so many different concepts that are layered on top of one another. But I think if you've been able to follow this video and understand what's going on here, you should have a pretty good grasp of mineralogy. So, thanks again for watching, and have a great day.